Okay, I'm back. If someone can confirm that you can hear me, then we can pick up again. Can anyone hear me? Okay, you can hear me. Okay, so we have another 20 minutes or so. Actually, we've got 15 minutes, but I'm going to talk until I'm done with the slides that I wanted to present, and I think it may take a few minutes more than that. So I want to suggest to the people who had questions that we leave them either till the end of this session. If we have time, we can talk about them. And if we don't, we discuss them in tomorrow evening's slot, which is, I think, at 6. Okay, we've got 45 minutes there tomorrow evening at 6. It's probably a good idea to give more people a chance to read through the material and see what they don't understand. So, with that said, I think let us continue with the presentation and we answer some questions tomorrow evening or afterwards. Okay. So the next example is example 11. Please understand this lecture is a long one. This week's material is quite long, but it's not. The material for next week, for all the other weeks, will be a little bit shorter. So there's example 11. The question is, for which values of R is the sequence R to the n convergent? Okay, now again, we go back to section 2.6 and we look at the graphs of the exponential functions. So remember, the exponential function looks like this: a to the x, where a is some fixed base. So it's similar to what we have here, because R is now the fixed base and the variable is in the exponent. So it's an exponential function and we let x go to infinity. Now we know, okay, I'm going to just check if everything's okay, because I seem to get, we can't see. Okay, my mistake. That should be better. There we go. Okay, so you haven't missed anything. Example 11, for what values of R is the sequence R to the n convergent? And so again, we go back to a similar example from last year, from section 2.6, and the graphs of the exponential functions, right? We had that function a to the x, which was called the exponential function. It's exponential because the variable is in the exponent and the base a is the same. So we know that the limit as x goes to infinity of a to the x is infinity. That's if a is greater than 1, right? And so the limit as x goes to infinity of a to the x is 0 whenever the base is in between 0 and 1. It's material that we covered in the 1A module last year. And so we can use Theorem 3 that we did in this lecture or in the previous lecture and see that the limit as n goes to infinity of R to the n must be infinity if R is greater than 1, and it must be 0 if R is in between 0 and 1, right? It's also easy to see that if the base is 1, then we get 1 as the limit. In other words, 1 to the n is always 1. So 1 to the 1 is 1, 1 squared is 1, 1 cubed is 1, and so on. And so it converges there as well. And the limit as n goes to infinity of 0 to the n is also 0. And so we get the following result. If R is in between -1 and 0, then the absolute value of R is greater than 0 and less than 1. And so the limit as n goes to infinity of R to the n absolute value is the limit as n goes to infinity of absolute value R raised to the power n must be 0. Right? So that's if the value of R is in between -1 and 0. And so the limit as n goes to infinity of R to the n is 0 by theorem 6. And there's a picture that shows you what these different sequences look like for various values of R. So if you look at the picture on the left, the graph on the left, the blue dots show you what the sequence does when R is greater than 1. Then the value of the sequence becomes larger. It becomes larger as n becomes larger, and the sequence diverges to positive infinity. When R is equal to 1, you get the black dots. So all of those have value equal to 1 because 1 to the 1 is equal to 1 to the 2 is equal to 1 to the 3 and so on. It's all always equal to 1. And the value of R is in between 0 and 1, then the sequence converges to 0. Right? Similarly, look at the picture on the right-hand side and notice that it shows you what happens when R is less than -1. Then the sequence will diverge to negative infinity. Right? If R is in between -1 and 0, you get the pink dots. Okay. Actually, when R is less than -1, you get that the blue dots will jump positive and negative. So there's actually a top part to that blue graph as well. Right? Definitely the sequence does not converge. Okay, so this result is important, so we need to summarize it into a theorem. The sequence R to the n is convergent if R is strictly greater than -1 and less than or equal to +1. And it's divergent for all other values of R. In other words, values outside of that range. So when R is larger than +1 or less than or equal to -1. So the limit as n goes to infinity of R to the n is 0 if R is in the range -1 to +1. It is equal to 1 if R is equal to 1. And it diverges for all other values. Right? And now we come to a very important concept. Right? The next set of concepts are, like everything else, important, but now we're moving to proving a very important theorem. So last year in Calculus 1, we also spoke about sequences being about functions being increasing and decreasing. And so a function was increasing if, when we drew the curve, it moves up as x becomes larger. It's decreasing if it moves down. The same thing for sequences. So technically or mathematically, we express this as saying a sequence an is increasing if an is less than an plus 1 for all n greater than or equal to 1. In other words, if a1 is less than a2, is less than a3, and so on. So as I make the index larger, the value of the function gets larger. If that happens, the function is called increasing. Well, of course, if you can have an increasing function, you must also have decreasing functions. So a sequence is called decreasing if an is larger than an plus 1 for all n larger than or equal to 1. We use a single term to describe a sequence that's either increasing or decreasing. Either increasing or decreasing is called monotonic. So if I say a sequence is monotonic, I mean it is either increasing or it's decreasing. Remember, it can't be both. Okay. So let's look at example 12. And we're going to show that this is a decreasing function. And we're going to prove it using the condition that you see in front of you now. We're going to prove that an is less than an plus 1 for this function. How are we going to do this for the sequence? And so we're going to say 3 divided by n plus 5 is greater than, notice what I'm doing now. I'm making in the second, in the expression on the right of the greater than sign, I've increased n to n plus 1. And so that's true because I'm dividing by a larger number. So 3 divided by n plus 5 must be bigger than 3 divided by n plus 1 plus 5 because I've got n plus 6 in the denominator now. And so I know that an, remember what I'm starting with is an. 3 divided by n plus 1 is an. And 3 divided by n plus 1 plus 5 is an plus 1. And so I've shown that this is a decreasing function. Show that this sequence is decreasing. Let's look at one way of doing it. We must show that an plus 1 is less than an. Okay, in other words, we must show that n plus 1 divided by n plus 1 squared plus 1 is less than n divided by n squared plus 1. Notice that that's going to be the case if and only if I can cross multiply and get an equivalent condition. So I can multiply the n plus 1 by n squared plus 1. That must be less than n times n plus 1 squared plus 1. And that's so I can simplify the terms on both sides of the less than sign now. I multiply them out, and I can cancel them and get that n plus 1 divided by the thing I started with is less than n divided by n plus 1, if and only if 1 is less than n squared plus n. But that's true because n here must be greater than or equal to 1. We're talking about a sequence. So the smallest value of n is 1. All right? And so that last condition is always true. And so the first condition must be true. And so this is an increasing function. Okay? Sorry, this is a decreasing function. What about the second solution? Here we're going to use calculus, right? So if we look at the function f of x is equal to x divided by x squared plus 1, what we've now done is we look at the same expression an equals n divided by n squared plus 1, but we now extend it to become a function of a real variable. If f of x is x divided by x squared plus 1, we're going to use calculus to show that this is a decreasing function. And so we do that by taking the derivative. Because we've got a quotient, we're going to use the quotient rule. So we say the derivative is the denominator squared, the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, which gives me 1 minus x squared divided by x squared plus 1 squared. Now we need to convince ourselves that this expression, this last one, is always negative, at least for x greater than or equal to 1. And that's easy to do because we look at the denominator and we see that the denominator is always positive. Right? So the sign of the first derivative is unaffected by the denominator. The denominator is always positive. And so the derivative is negative whenever the numerator is negative. And when we do that, we see that we get the condition that x squared must be greater than 1. And thus, f is decreasing on the interval 1 to infinity. And so f of n is greater than f of n plus 1. Hence, the sequence AN is decreasing. Next definition. A sequence is bounded above if there is a number m such that AN is less than or equal to m for all n greater than or equal to 1. We call this m an upper bound for the sequence AN. A sequence AN is bounded below if there is a number lowercase m such that lowercase m is less than or equal to AN for all n greater than or equal to 1. This number m is called a lower bound for the sequence AN. A sequence which is bounded above and bounded below is said to be a bounded sequence. I'm going to go through this definition again. We will say a sequence is bounded above, a sequence AN is bounded above if there is a number m such that all the elements from the sequence, all the values of the sequence are always less than or equal to this number m. So it's an upper bound. This m is an upper bound for the sequence. The values of the sequence never go above m. Right? They can be equal to m, but they never go larger than it. Similarly, a sequence is bounded below if there's m, a number which is such that the sequence can never go below that value. And that lowercase m is called a lower bound. If a sequence has an upper bound and a lower bound, then it's called a bounded sequence. Now, we're going to extend this concept. This concept that I've shown you now is strictly speaking, it's only defined for a sequence, which is a function. But it's easy to see that we can extend this concept to any set, any subset of the real line. And so in the next example, I'm going to do that. We extend this concept of an upper and a lower bound to arbitrary sets, as in the example below. We notice that if a set has an upper bound or a lower bound, it will have many of them. So let's have a look. Suppose the set S is the interval 0, 1, where I'm including the left endpoint. So I include 0, but I exclude 1. Then it's easy to see that 1 is an upper bound of S. Well, what's the definition of an upper bound? Remember, for 1 to be an upper bound, it means no element of the set, or every element of the set S, must be less than or equal to 1. That's the case here. So remember, this interval, the set S, is by definition all the set of elements in between 0, including 0, and 1, excluding 1. And so 1 is an upper bound of S. But also 1.5 and 2, these are all upper bounds. Similarly, the numbers 0, -1, -2 are all lower bounds of S. And so we can see that if a set has an upper bound, it will have many. If it has a lower bound, it will have many, right? So if you think through this, when you read through the notes, see if you can come up with a number which is not a lower bound and not an upper bound for the set S. We're going to work with this for another example until we prove a very important theorem, and so that I can explain to you a very important property of the real line, right? We need another definition. If S is a subset of the set of real numbers, then an element M0 is called a least upper bound of the set S if it satisfies the following two conditions. The first one is M0 is an upper bound of S, and if M is any upper bound of S, then M0 must be less than or equal to M. I'm going to say it again. Let S be a subset of the real line. An element M naught, a real number, is called a least upper bound of the set S if it satisfies the following two conditions. Condition 1, it must be an upper bound of S. And I've just defined upper bound. And condition 2, if M is any upper bound of S, then M naught must be smaller than that M. We've got a parallel concept of greatest lower bound. So least upper bound, greatest lower bound. We call an element lowercase m naught in R a greatest lower bound of the set S if it satisfies the following two conditions. M naught is a lower bound, and if M is any lower bound, then M naught must be greater than or equal to M. So you need to go and think about this carefully, because if you think about it, you will be able to see exactly why we call a least upper bound that name. It's the least of all the upper bounds. So earlier we said it's clear that if a set has an upper bound, then it will have many. Right? If M, capital M, is the upper bound of a set, then any number bigger than M must also be an upper bound. And so the concept of least upper bound makes perfect sense, because since it has many upper bounds, we are interested in the smallest number, which is an upper bound, but smaller than all the other upper bounds. Okay? Let's look at another example. Let S be the open interval 0, 1. So this includes all numbers larger than 0 and less than 1. Now the real number 2 is an upper bound of the set S. Again, the real number 1.5, again, is an upper bound of the set. Does the set have a least upper bound? Well, I'm going to convince you now that the number 1 is in fact the least upper bound of that set S. Now, notice firstly that the number 1/2 is not an upper bound of S. It can't be an upper bound because the number 3/4 is in S and a half is less than 3/4. Remember, for half to be an upper bound, all numbers in S must be less than or equal to it. And so a half cannot be an upper bound. What is the least upper bound of S? Does S in fact have a least upper bound? When do we know that a set has a least upper bound? Let's show you that 1 is the least upper bound here. So S again is the set 0, 1. And by definition of interval 0, 1, we have that A is in S implies that A is less than 1, which means A is less than or equal to 1. And so 1 is an upper bound. 2. Suppose C is any number which is less than 1. We will show that C cannot be an upper bound. Now, either C is in S or C is less than or equal to 0. Suppose it's less than or equal to 0. Well, then half must be bigger than C, and C cannot be an upper bound for S. Because for C to be an upper bound, it must be larger than or equal to 1/2. Suppose that C is in S. Then I'm going to pick a number in between C and 1. How do I pick that? Well, C is less than 1, right? So 1 minus C is a positive number. I divide it by 2 and I add it to C. Now I know this new number must be in between C and 1. And so C cannot be an upper bound because I've generated a number which is in S but larger than C. Hence, we have shown that if C is any upper bound for S, then it must be greater than or equal to 1. 1 and 2 above mean that 1 is the least upper bound of the set S. Another example. Suppose that C, another thing to note about least upper bounds. Suppose that C is a real number is the least upper bound of the set S, subset of R. Let B be in R so that B is less than C. And it should be clear from the definition of the term least upper bound that B cannot be an upper bound of S, right? Because it's smaller than C. Now, we can state the same thing as follows. If C is a real number and it's the least upper bound of a set S, let us pick an epsilon small now, any small real number epsilon. Then C minus epsilon must be less than C. And so C minus epsilon cannot be an upper bound. Because remember, C was the least of the upper bounds. So if I make it smaller, any number smaller cannot be an upper bound. But if that's the case, then by definition of an upper bound, we must be able to find an S in S with a property that C minus epsilon is less than S, which is less than or equal to C. Now, this property of an upper bound, of the least upper bound, is very important. It's going to come up in the theorem, the first theorem that we prove, that you must know the proof of, which we do next. Okay? And first, before we prove the theorem, we have this property of the real numbers called the least upper bound property. So earlier I said to you, how do we know that a subset of the real line has a least upper bound? Well, here is the condition. This is called the completeness axiom of the real line, or the least upper bound property of the real line, and it says every non-empty set of real numbers that is bounded above has a least upper bound. Now, once we know that this happens, we can use this property to prove that that the set of real numbers also has the same property in reverse for greatest lower bounds. Right? It says every non-empty set of real numbers which is bounded below has a greatest lower bound. And now we can prove the following theorem. The monotonic sequence theorem, which says every bounded monotonic sequence is convergent. Now, the word monotonic, like you saw earlier, could mean either increasing or decreasing. So we will prove the case for an increasing sequence. The proof of the case for a decreasing sequence is left to you to write out as an exercise. So let AN be a sequence that is bounded above. Since it's bounded above, the set S equal to AN, as n runs through the set of natural numbers, is bounded above. By the least upper bound property, S must have a least upper bound. Let's call that L. Now, if I give myself an epsilon positive, then L minus epsilon is not an upper bound for S. That's the case because L is the least upper bound. Any number smaller than it cannot be an upper bound, right? And so there must exist a stage in a natural number with the property that AN is bigger than this L minus epsilon, but still less than or equal to capital L. Next, since the sequence is increasing, we have that n is greater than n, means that AN must be greater than a capital N. Right? That's the definition of in an increasing sequence. Thus, if n is greater than capital N, then a lowercase n is greater than L minus epsilon. So that L minus AN is greater than or equal to 0, which is less than epsilon, since AN is less than or equal to L. So that last bit, since AN is less than or equal to L, proves that L minus AN is greater than or equal to 0. That's where we need it for. Now, we've shown that the absolute value of L minus AN is less than epsilon whenever n is greater than n. And thus we've shown that the limit as n goes to infinity of AN is L, as we wanted to prove. Now, we've shown this, right, for a sequence that's increasing. Prove the corresponding thing as an exercise for a sequence that's decreasing. Okay, I'm going to stop here. We can have a session tomorrow evening to look at your questions relating to material that we've done so far, and I will leave example 14 for next week. Okay, there's still a little bit to be done. We can do it next week. Just before you go, I am probably going to start recording lectures, which I will post. The lectures, I don't want them to become too big, so you'll probably have a few files, a few video files to download for a particular lecture. Okay, we'll leave it there. Let's have a look at some of your questions. And I've had one person. The tutorial questions will be posted in the next half an hour or so. My period is over. Yes, I know. And I will see those of you. I'll post an announcement tomorrow evening. Those of you who want to come along, feel free and watch the announcements for some admin information around what will happen with tutorials going forward. Okay, Mr. Naika, tutorial questions will be posted in the next half an hour. Okay, cheers. Thanks for coming.